All right. Here we go. And here we go. Display settings. There we go. All right, so today we're going to be doing the introduction and review. So I'm hoping that the majority, say 90+% of my lecture today is review. And anything in here that you may be having trouble with, get it under control ASAP, because a lot of the stuff in this introductory slideshow here is very fundamental to learning organic chemistry. What happened? I'm not sure what just happened there. All right, so what is organic chemistry? It's the study of natural foods, right? Just kidding. It's the study of carbon-containing compounds. It's extremely important because carbon is literally everywhere. And as I mentioned earlier, I like to think of carbon as being like your ultimate Lego piece. Like it can connect to any other piece. It's extremely important for life. The way so you always hear that the human body is composed mostly of water. The analogy I like to think of is that yes, our bodies are mostly water, but our carbon pieces are the water balloon itself, holding all the water together. So all the structure and function, all that's carbon-containing compounds. All the fluids, that's all aqueous stuff. There's my general version of A&P for you. What is organic chemistry? So it turns out that back in the olden days, people called it vitalism. And the main reason why people called it that was they believed that in order to make a carbon-containing compound, that it had to come from a biological source, and that it had some magical energy that was like imbued into it to make it exist. This guy, Frederick Wohler, did find out that that is not the case for certain compounds. And he took ammonium isocyanate, which is technically from an inorganic source, and found if he heated it, it turned into urea. Which you guys probably guessed, that is the main constituent of urine. Just a little side note here, if you ever get drug tested, one of the things they look for is they actually look for urea. And that's to see that whatever your sample was is actually urine. So main constituent of urine that obviously comes from a living source, but hey, we can make it from an inorganic source. And then after this guy figured this out, many chemists after him did other examples of this. So it shortly became called organic chemistry instead. So the vitalism kind of stuck with it a little bit, but we changed the wording a bit. Carbon is pretty important in all biological compounds. All pharmaceuticals are organic in nature. They're also used in plastics and synthetic materials. I think your desktops that you're sitting at are actually made out of plastic. So those are organic. And things that we consider to be inorganic carbons are things like carbon dioxide and their derivatives. So we have carbon dioxide carbonates, bicarbonates, isocyanates. Those are all inorganic stuff. They will show up here a little bit, but pretty much everything else is considered organic. So that's why people generalize it into the chemistry of carbon, but technically carbon dioxide is inorganic. We're going to be going over a few things here. This is basically the general overview of what organic chemistry is. We're going to be spending a big portion of this first semester going over physical properties, as well as spectroscopy and structure determination. We will be getting heavier into reactions and mechanisms about roughly halfway through, and then from then on it's pretty much just hardcore reactions and mechanisms until the end of the year. Organic chemistry 2 is nothing but reactions and mechanisms and reinforcing concepts from this semester. Lab techniques are pretty important. I think it's kind of interesting compared to most of your other chemistry classes. We will not actually be doing our first actual experiment until about lab 8. All the labs before that are teaching you how to do organic chemistry. So like our first lab this coming week is what, melting point lab. And you're going to see as later on we start actually doing our real experiments, you're going to make a compound in the lab, purify it via a method you learned how to purify earlier, and then you're going to get a melting point to assess the purity of it. So it all kind of just builds up to each other. But yeah, it's about lab 8, I believe, that we stop doing techniques, start doing actual experiments. Oh, on that note, the lecture and the lab do not really correlate very well until then. So the stuff that we're doing in class now, we're not even going to talk about it at all in the lab. Carbon is found in a large abundance in nature. It comes from the Latin word for coal, element number 6, and I say here that it's tetravalent, meaning that it likes to form 4 bonds. And there's a bunch of different variations of the way it can form 4 bonds, giving it a huge amount of variety. There's infinite amount of variety that carbon compounds can form in different shapes they can make. Here are the different isotopes of carbon. This is somewhat important later on in the semester. So basically, later on, we're going to be doing a form of spectroscopy where we're actually going to be looking at carbon-13s. The main thing I want you to take away from this here is that carbon-12 is the most abundant. And I thought it was pretty cool that I found this picture on the internet because it has carbon-14 listed there and what it's used for. Super, super small text, but it says quantitative tracer of fossil fuel CO2 emissions. So part of my work in graduate school, as I was looking at air quality in Fairbanks, Alaska, and what we were doing is we were pulling in soot from the air there because the air there is completely nasty during the winter. So basically what happens in the winter there is that they're in a mountain valley and they get inversion events. And an inversion event is when you basically have a bunch of clouds holding all the air in place. The air doesn't have anywhere to go. And because they're in Alaska, they don't have natural gas lines and whatnot, so they're burning a lot of diesel fuel to keep warm in their homes. They call it fuel oil there. And they're also burning wood, and that smoke has nowhere to go. So it all just kind of builds up in the air. And what my job, or what our group was doing, we were taking these filters that they were basically sucking in this big tube, sucking in air for a couple hours, sending little filters to us, and they cut it into little sections. And one of the sections used to go to a different lab to measure the C12 to C14 ratio. And the reason why that's important is because C14 does occur naturally, very low amounts, but it's radioactive, meaning it decays. So what that tells me is that if it has a C14 ratio equal to the carbon-14 that's in the atmosphere from our CO2, that means that whatever plant material or whatever was burned to make that smoke died recently. And if there was mostly carbon-12 in there because all the C14 decayed, that means that whatever organism that fuel came from died a long time ago. So why would that be relevant? You guys think? Like, what is the significance of having a fuel that died recently versus something that died a very long time ago? Well, that's not necessarily carbonated. We're basically saying, okay, did that smoke come from a tree being burned, or did it come from coal being burned, or oil, crude oil? So it turns out that things like gasoline, crude oil, diesel fuel, all that kind of stuff has really low to none carbon-14 because it died, hundreds of millions of years ago, or however long ago. Definitely a lot less than what you see in, say, burning a piece of wood. And my particular job for that project was to look at specific tracer molecules for different types of fuel sources. So it turns out they can also extend this for particular compounds always come from particular different fuel sources. And I was looking at diesel fuel smoke, basically, for most of my work to add to the project. So not testing it on that, just throwing a little bit out there about my background. Did a little bit of climate study stuff while doing organic chemistry. It all kind of ties together, right? All right, why is carbon so special? It does have 6 total electrons, meaning that we have 2 in the s orbital, and then we have some in the p orbitals. Basically what can happen is that these orbitals can align to allow us to have 4 bonds total, meaning it's tetravalent. I do mention the electron configuration in here. This is about the only time this semester I'm going to mention electron configurations. We don't really go over configurations in this class. So if you don't remember that stuff, don't worry about it. But you do need to know that carbon can form 4 bonds. These are the main ways that you're going to see carbon forming 4 bonds. So we have the tetrahedral, we have the trigonal planar, linear, etc. So I do have a few comments there. You're going to have to remember the different shapes they can make. So if you have something that has 4 bonds to it and no non-bonding groups, that's a tetrahedral. And then that particular carbon atom is an sp3 hybrid. I go over this a little bit more detail later in the PowerPoint, but I'm hoping you guys remember this wording and the shapes. And the thing is here is that shapes matter. So when you guys draw a tetrahedral, notice how on the left drawing there, the tetrahedral, how we have the two that are in the plane, two that are out of the plane, how they're like on one side of the molecule or the other. That's the way you want to draw it. You don't want to draw it like this, where you have like a line in the middle, and then you have like a wedge on one side and a dash on the other. That is not correct. This does actually matter, because later on we're going to be talking about chirality, handedness of molecules. These don't look like the right hands. You will get wrong answers sometimes. So just get in the habit of drawing tetrahedrals correctly, and I'm actually very picky about shapes in this class and the way you draw them. So oftentimes I will correct a drawing on a test, and I won't actually mark off for it, but I'll correct a drawing a lot of the time. All right. Oop. So Lewis structures. So I'm hoping you remember some of your rules for Lewis structures. You guys, I know, and when I teach 121, I go over the NASU method. We don't really use that all that much in organic chemistry because we're working with larger molecules. And the way we approach Lewis structures is a little bit different than the way we do in general chemistry. The main thing we focus on is things like satisfying octets and making sure that we have the right number of electrons to get the corresponding formal charge. You guys remember doing formal charges? We'll definitely review it here because they're pretty important. So in short, the number of valence electrons available to you is whichever column in the periodic table it's in. So carbon, being that it's in group 4, it has 4 available. In general, for this pretty much, I basically just put the full rules here for Lewis structures. So first things first, you should determine the number of valence electrons. We're not going to be focusing on that all that much when we start getting organic compounds. There are ways to kind of get past these rules in a quicker manner. Determining the arrangement of the atoms. We are going to be focusing a lot on functional groups and how those fit together, as well as naming, because carbon is so variable, there's a variable amount of ways you can put these compounds together. So the names and all that come into play as well. The big thing here, though, is that you are satisfying octets. In the case you have a 0 formal charge, you should be satisfying octets, meaning everybody has 8 electrons total. And in the case where you have a non-zero formal charge, you have the correct number of electrons on there, which we'll see here in a few minutes. Also recall that single bond atoms form 1 pair of electrons, and then if you have a double bond, that's 4 electrons, 3 bonds, that's 6 electrons. But I'm going to ask you guys here, what is the first bond between atoms called? It's called the sigma bond, and what are the additional bonds called? Pi bonds. Do they remember the difference between the way pi bonds and sigma bonds look relative to each other? So the sigma bonds were the ones that were along the axis between 2 atoms, and then you had the pi bonds that were kind of above and below, right? We have pictures in here. Don't worry. Getting ahead of myself. It's a little joke amongst organic chemists. This is the organic chemistry periodic table. This is about all we're going to look at. There are certain times where we're going to be talking about things like lithium and sodium, but they're more often than not they're spectator ions. Typically, the chemistry is going to involve hydrogen and your non-metals. So all your halogens, oxygen, sulfurs, nitrogens, phosphorus. So if you're going to basically commit anything to memory, by the time you guys get further along in this course, you guys are going to know the valence electrons of all these elements without even thinking about it. You're just going to have done so many problems right now, you're going to go, halogens have 7, without even looking at a table. And you'll probably know it's a halogen without even looking at the table as well, because we're going to be working with these elements a lot. Something interesting I want to show here is that silicon is actually directly below. And as you guys know, silicon actually does have a lot of properties of carbon. And there are some cheesy science fiction theories out there about silicon-based life being a possibility, but we'll see. But it's all based off the fact that it's right below carbon, and we know that carbon is responsible for life. All right, here I just have a summary of their valence electrons and their Lewis dot structures. In general, the way you want to think about the way that these fit together is that you have these pairs of non-bonding pairs, but the lone electrons can actually form a bond of something else. So we're going to see that things in the same column on the periodic table are going to make the same types of compounds. So for example, there's just carbon having 4 bonds and silicon having 4 bonds. And so on and so on. Okay, here are some examples of Lewis structures here. This particular page was putting a focus on counting the valence electrons. As you guys are getting started off, these simpler compounds, that is something you're going to do. But as we progress later in the semester, we're going to put more of a focus on formal charges and counting bonds. And there's a table here that you are going to commit to memory whether you like it or not. Because it's just with the repetition, you're going to remember this stuff. In general, though, right here I have a listing of all the different main elements we're going to work with and how they will be bonded in an organic compound and have a 0 formal charge, meaning they have no charge on them. So hydrogen has 1 bond to it, carbon has 4 bonds, nitrogen 3 bonds and 1 lone pair, etc. And if you compare it to the previous table, here it kind of lines up. So it said on the other page that nitrogen has 3 bonds and 1 lone pair. You may see here that nitrogen, being group 5, has 5 electrons available, so it has 1 pair and 3 singles, which can then go out to make bonds to other atoms. All right, here's another way of presenting the same information. This is basically how many bonds you want to have such that they are neutral. As you guys are getting started off in drawing Lewis structures, you are going to want to draw in all of your electrons here. But as we get further in the semester, you probably start dropping them off for the sake of simplicity. But you need to fully understand in your brain what's happening before you start making things shorthand, right? So you don't want to start shorthanding things so you fully understand what is going on, because that can lead to wrong answers. All right, formal charges. In compounds, charges can be assigned per atom. And recall that the overall charge on the molecule is the sum of all the formal charges. So just because you have a compound that has an overall 0 charge in it does not mean every atom in there has a charge of 0. And this may include, to calculate the formal charge, you must have a valid Lewis structure. There are a few rules of things that we want to avoid. Basically, you don't want to violate octets, things of that nature. Having unfilled octets on bad atoms, that kind of thing. This does include bonding and non-bonding electrons in the calculation. Here is your general equation. So the formal charge is equal to whichever group it's in, minus the number of bonds and the non-bonding electrons. Where did my pencils go? There we go. I think I do have an example. Here, nitrate ion. So it says here the nitrate ion, for example, overall nitrate is what, NO3 minus, and it overall has a -1 charge, meaning that when I add everything all together, it should all equal -1. So I just want to go like one atom at a time here, see if you guys can help me out. So I'm just going to go ahead and redraw this here on this paper, switch to the camera. So let me go ahead and draw on here first, and then I'll fix the focus if I need to. Looks like I do. Probably should fix the lighting as well. All right. Oh, one thing I want to mention here is that, oops, what the hell? Oh my God. This is frustrating. Oftentimes when drawing out organic compounds, you may remember from your general chemistry class, we put the little brackets around it with the minus charge. We don't do that all that much in organic chemistry. That seems to be more of a Gen Chem thing. We do know that overall this is NO3 minus 1. If anybody knows how to fix that, I would gladly take some advice from that. All right, so what I want to go ahead and do is take a look at this formal charge for that oxygen atom. So if you don't remember, oxygen is in group 6. We're going by the Roman numerals on the periodic table here. So 6 minus, and then you go ahead and count the number of bonds. There are 2 bonds, so it's minus 2. And then we have 4 electrons here, so minus 4. So overall, that has the charge of 0. Using the same type of logic, what do you guys think the charge on nitrogen is going to be? Positive 1. Yep. So nitrogen is a group 5 element. It has 1, 2, 3, 4 bonds. So minus 4, and we don't have any non-bonding electrons, so that is plus 1. Oh my goodness, like every 2 seconds it does that. All right, there it goes. All right, so we can then take a look at this oxygen. This is so frustrating. I really don't want to have to go back to using the regular .chem because it has really low resolution on it. All right, what do you guys think? Negative 1? Yep, so it is a group 6 element. And then we see that we have 1 bond, so minus 1. We have 6 non-bonding. One of the things you want to be careful of here, so I'm counting each bond as a 1, and then each individual non-bonding. So the biggest thing here I've seen students do, if they're going to make a mistake, is they will count the bonding groups as 2 electrons. You'll just count it as 1. So here we have 6 minus 1 minus 6 is negative 1. This one has the same overall setup there. Oh my God. I'm going to be face palming all semester with this. All right, so then if you add everything together, we have a plus 1, a minus 1, and a minus 1. Overall, it's minus 1. So the point we're going to get to in this class, and I'm hoping you get here sooner than later, is that when I personally see a oxygen that has a single bond and 3 lone pairs, it's negative 1. I don't even calculate it. I've just done it so many times that you memorize it. And don't worry, like you guys are gonna memorize the common formal charges throughout the semester. The cool thing about learning these common formal charges is that they're always either plus 1, minus 1, or 0. If you're getting something that's either like a minus 2, minus 3, or plus 2, plus 3, those are high energy structures usually, and you want to try to avoid those kind of structures. So thankfully it's not as bad as it sounds, because they're all going to be plus 1, minus 1, 0, and there's only going to be a handful of different elements that we're going to be looking at anyway. All right. Duplicate slideshow. All right, so this is doing the same thing here. It shows you the math that we went through. Do that for each of the individual atoms, and then add it all up, and that is your overall charge. Okay, so here's a little short table here on the different, just for carbon, nitrogen, and oxygen. Not having to calculate the formal charge and going by pattern recognition is going to save you a lot of time in the long run. And that's actually a big theme in this class overall, is pattern recognition. And I like to point out patterns as we come along. And you're going to see, especially next semester, I'm going to refer to things as being like this thing from OChem 1. And we're going to be using a lot of that stuff as we go along. So pattern recognition is big. So if I were you, I would try to commit this to memory, especially at least for carbon, nitrogen, and oxygen. These are pretty common. The other thing I want to point out here too is that when students are drawing out Lewis structures for their first time, especially with organic compounds, there's this impression that everything has to have a 0 formal charge. That is not true. They can be non-zero, even on carbon. Okay, I am not going to go over all of BSEPR. I'll give you the shorthand. Basically, what happens when compounds are formed is that the bonds and non-bonding and bonding groups will arrange such that they are as far apart from each other in physical space as possible, or in 3D space. And the result of that is that after you get past 3 groups, the object is no longer flat. It becomes 3-dimensional. Because if we have a tetrahedral here, if you wanted it such that, if it was flat, everything would be 90 degrees apart. And then if we put it in 3 dimensions, they then widen a little bit. You remember what that bond angle was? The bond angle for a tetrahedral. 109.5. So by broadening it a little bit into 3 dimensions, we're able to get a little bit further apart. You might want to recall the bond angles. Additionally, when we start having extra groups on there, or non-bonding groups, the way we look at it is electronically, if it has 4 groups on it, it's a tetrahedral. But we look at the overall shape, we no longer consider that non-bonding group as part of the overall shape. So for example here, if we have 1 bonding group on there, that is a trigonal pyramid. And then if we have 2 non-bonding groups, that is a bent or V shape. And then I went ahead and included all of BSEPR on here. We are not going to go past a tetrahedral. So this is just here to be complete, but when you get into studying, just focus on tetrahedral and up. Those are the ones I want you guys to remember. So we're not going to be drawing those octahedrons or anything like you've never doing that stuff in Gen Chem 2. We're not doing that stuff in here. There is like one time where a trigonal bipyramid comes up, but it's kind of a weird little example that I go through. Just say, hey, it's cool looking. All right, we did already kind of talk about this, but the reason why I want to bring it up again and why hybridization matters is that we can actually look at the hybridization of an atom, and if in the case of carbon, we can kind of predict some reactivity of it. So for example, I know that carbon with a double bond is nucleophilic. What does that word even mean? That's the whole part of organic chemistry being a second language, right? But you're going to learn a lot of vocabulary as the semester progresses, but I know just looking at an sp2 carbon, it's going to react a certain way. Also depending on what else is attached to it. And we'll definitely go how to predict these kind of things, as we go along and start going over the actual chemistry of carbon. I do mention here also that we can use different types of spectroscopy to tell the difference between different carbon types. We also use spectroscopy to figure out the structure of molecules. So we're actually going to be starting the first one next week. That is for infrared spectroscopy. We do have an infrared spectrometer in each of the labs at CSN. And basically what that allows us to do, we can actually physically see functional groups in them. You remember learning your functional groups in probably your biology courses. We are going to go over those again next week, and they're pretty much the same ones you learn in your bio classes. The extra part we're going to add on to it is how to see them in lab. So we traditionally in the past, like back in 1800s, they were doing chemical tests to see them. Now we use instrumentation to see them. It's actually plain as day when there's like a carboxylic acid there or not. So we'll see all that stuff next week. All right, we talked about this already. Bonding and orbitals. So essentially what's happening with bonding here, so I do have a little bit of MO theory stuff here. The main thing that I want you guys to take away from this is the sigma bonds and pi bond discussion. So essentially when a bond first forms between 2 atoms, they will form a sigma bond, and then that is along the center axis of the 2 atoms. When you have sigma bonds, they are the result of the formation of hybrid orbitals. Basically what hybrid orbitals are combinations of atomic orbitals. You may remember learning about your S's and your P orbitals. Those can combine and form combination orbitals, which are basically a hybrid of the ones that are involved here. So here I have the sp3 orbital, hybrid orbital drawn there. Once again, the sigma bonds are the hybrid orbitals. If there is a pi bond there, they are from any leftover p orbitals that are not part of the hybrid. And we can actually tell the hybridization by number of groups that are bonded on there, right? So it kind of all goes hand in hand here. All right, so if we have 4 groups that are bonded, so basically you look at the center atom, you look at the number of electron groups on there. So electron groups include bonding groups and non-bonding groups. So basically you have to get a Lewis structure first before you can figure out hybridization. After we have that, we see there's 4 bonding groups on there. We know that it's going to form a tetrahedral and make 109.5 bond angles, no pi bonds at all, because all of the s's and p orbitals are tied up in sigma bonds. Here I'm just showing you the geometry a little bit drawn out. This is why we call it a tetrahedron, is because that is that shape there. And the nerd in me sees the 4-sided die, you know? But that is technically a 4-sided die. They do exist. Just more drawing the same thing. Just figured out all the different representations. So out of the 3 drawings on the bottom, which one do you think is the most real drawing, or the most realistic drawing? The one on the far right. So that is a space-filling model. So when you guys see the tetrahedral, that's the actual shape that they're making. But when we draw them out, we draw them the other way with these lines here to give us a little bit more detail. All right. And I think this will be about where we stop, and we'll pick up with hybridization, all that next time. I do want to mention here that I do feel like I'm going kind of fast with this stuff, but my hope is that this is all review. So will this review for you guys? Or you're not learning anything new today yet? All right. So if you guys have any questions or anything, I mean, we are finishing a few minutes early. First things first, before I let you guys go, I wanted to ask who here is in my afternoon lab?